Okay, welcome back. We're moving on to the next section. This is variational autoencoder. We have seen in the previous chapter the autoencoder architecture. As a quick recap, it is an encoder decoder architecture that aims to generate the same output as the input. However, by making the data go through a lower dimensional space, the latent space, and forcing the decoder to reconstruct the input signal from that latent vector properly, it effectively learns from a reduced set of variables. The variational autoencoder introduces a new ingredient in the latent space section. Instead of using the output of the encoder vector in the latent space to feed the decoder directly, it uses the output of the encoder to feed the generation of new data out of a distribution for which the average and standard deviation are the output of the encoder to vectors. The idea is that this new data, as it is supposed to belong to the same distribution in the latent space as the output of the encoder, somehow assumes that it represents the same data. If we feed an observation generated from that distribution in the decoder, we will get an output very similar to the input data. So I think this works to put it into ChatGPT. I don't know, maybe it's just kind of a waste of time, but I'm kind of typically pretty impressed by the responses.
The image you uploaded depicts a variational autoencoder, VAE, a type of deep learning model that is designed for generative tasks, meaning it can learn to generate new data that resembles the input data. Here's a breakdown of the components and how this model functions. Components explain. Encoder. The encoder part of a VAE takes input data and transforms it into two separate spaces, one for means, mu, 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 and one for standard deviations, sigma, sigma, sigma. These parameters describe a probability distribution for each dimension of the latent space. Latent space and reparameterization trick. The latent space in a VAE isn't fixed. Instead, each point is described probabilistically by mu, 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 and sigma, sigma, sigma. The reparameterization trick involves sampling from a standard normal distribution and then scaling and shifting the sample with sigma, 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 and mu, mu, mu respectively. This allows the model to backpropagate through random operations, facilitating learning. Decoder. The decoder takes these sampled latent points and reconstructs the input data. The goal is to minimize the difference between the original input and its reconstruction, thereby training the model to understand and generate new data that resembles the training data. Loss function. The loss function in a VAE has two parts: a reconstruction loss that encourages the decoded samples to match the original inputs, and a regularization term that helps learn well-formed data distributions and improves the generativity of the model. Applications of VAEs. Image generation. VAEs can generate new images that look like realistic photographs or artistic pieces based on the training data. Anomaly detection. In scenarios like flood detection, VAEs can learn the distribution of normal operations and thus can detect anomalies when new data doesn't fit the learned distributions. Data compression. VAEs can effectively compress data into lower dimensional latent spaces and reconstruct it with minimal loss, useful for reducing data storage and transmission costs. How it works. The encoder compresses the input into a distribution over the latent space. Random sampling from these distributions adds variability to the latent representations, which is crucial for generative processes. The decoder then reconstructs the input from these varied latent representations, learning to fill in gaps from potentially noisy or incomplete input data effectively. This setup, especially with its probabilistic twist and a reparameterization trick, allows VAEs not just to learn the exact input but to imagine or generate new data points that are variations on what it has seen during training, making it a powerful tool for generative tasks.
Alright, I might need to take a break, but let's see. Okay, so I'll get to the next section. Therefore, while the autoencoder produced only 1 point per input observation in the latent space, it now produces one area determined by the mean and standard deviation vectors. By introducing noise as input to the decoder, it is now possible to generate vectors in the latent space following the distributions calculated, which will result in new data that is expected to be aligned with the input training data, but effectively new and unseen. The variational autoencoders can be used to generate, for example, new samples of a certain metric, traffic on a 5G cell, based on existing samples of that metric. New fake samples can be generated to help in simulation scenarios. Alright, so next one is generative adversarial networks. And I do need to take a break. I'll just feel a lot better if I do that. So should be back in 20 minutes or so. Alright, I'm back and I'm feeling much better, so let's continue with generative adversarial networks. Generative adversarial networks, aka GANs, are for me personally one of the most fascinating techniques available today to generate new data. They are behind many of the examples you may have seen ML models that generate pictures of non-existing people to generate realistic videos of non-existing locations, etc. The goal is to generate some type of data with a quality that is indistinguishable from the real ones. Incredibly realistic pictures of people that do not exist, for example. Alternatively, as we will see in one of the practical exercises, generate realistic syslog messages out of nowhere. Interesting. A GAN is not just one neural network, it is a combination of them. It is a compound architecture similar to the encoder-decoder architectures we have seen. In this case, there are two main components. The generator. The mission of this building block is to take noise as input and generate an instance of the data in the most realistic way possible. The discriminator. The mission of this building block is to take data observations as input and determine if they are real or fake. What is inside the generator or discriminator will be use case specific. If it is about images, very likely these are some form of CNNs, but if it is about a text, it may be other techniques. Alright, so hopefully see what the AI says about the AI. The way the GAN works is, number one, the generator produces fake data. Initially, it is very much random. Note that the generator will never see any sample of the real data.
The diagram you uploaded illustrates a generative adversarial network, GAN, a deep learning model used for generating new data that resembles the training data. Here's an explanation of its components and functionalities. Components of a GAN. Generator. The generator creates new data instances from random noise. Its goal is to produce data that is indistinguishable from real data, effectively fooling the discriminator. Discriminator. The discriminator evaluates data to determine whether it is real from the dataset or fake generated by the generator. It is trained to be able to distinguish between the two. Real data. This is the actual dataset from which the GAN learns. The discriminator uses this data to learn the characteristics of genuine data instances. Fake data. These are the new data instances created by the generator. The discriminator assesses these to help the generator improve its output. How it works. Training the discriminator. The discriminator is shown real data and data generated by the generator. It must learn to tell them apart, classifying real data as real and fake data as fake. Training the generator. The generator creates data and tries to get it past the discriminator as real. Over time, it learns from the feedback, essentially, how well it is fooling the discriminator, and adjusts to produce increasingly realistic data. Feedback loop. There is a continuous feedback loop where the generator improves based on the success rate of its data passing as real, and the discriminator gets better at distinguishing real from fake. Applications of GANs. Image generation. GANs can generate new images that look like authentic photographs, which can be used in gaming, film, and design to create realistic environments or characters without manual artwork. Data augmentation. In fields where data may be scarce or expensive to obtain, like medical imaging, GANs can generate additional data for training machine learning models. Style transfer. GANs can modify a piece of content to match a particular style, such as turning a daytime photograph into a nighttime one, or converting classical music into jazz. Super resolution. Enhancing the resolution of images using GANs is a practical application in video enhancement and medical image analysis where details are crucial. Conclusion. Generative adversarial networks represent a powerful tool in the AI toolkit, enabling the generation of new, high-quality data from existing data distributions. Their ability to learn and mimic complex distributions makes them particularly valuable in fields requiring realistic synthetic data generation.
Alright, so number 2 of how a GAN works, generative adversarial network. The discriminator is fed with labeled samples of real data and fake data from the generator. Number 3, the discriminator is trained to be able to differentiate properly when the input observation it has received is real or fake. It is basically a binary classifier. Number 4, the generator is trained with a partial view of the output from the discriminator. The more fake images are classified as real by the discriminator, the better is performing the generator. For example, the loss function will be lower. The 5th way GAN works is the process goes on. Progressively, the discriminator becomes better at differentiating if an input image is real or fake. At the same time, the generator becomes better at producing data that is more and more realistic, since its input is the output of the discriminator with the fake data. So if it is not producing good output, the discriminator can detect what is fake and wins, whereas the generator loses. On the other hand, if the generator becomes really good at producing realistic output data, the discriminator will fail at detecting it as fake, and that will force the discriminator to improve even further, etc. As you can see, it is a game between the generator and discriminator in which neither really wins. However, both will force each other to improve, which results in our goal: the generator to produce totally new observations of the data that look highly realistic. What I find really fascinating is how the generator, which is never exposed to any sample of actual data, can end up optimizing all its internal weights to generate realistic data out of random noise as input. We will see a working example of this architecture in the practical use cases to generate realistic log messages. New and more advanced architectures are being proposed and used that will supersede the capabilities of GANs, such as stable diffusion models. For now, I do not think you need to know about them because their applicability to our network and cloud field is still unclear, although possible, as we have seen with the GANs. Alright, so the next part is reinforcement learning. Reinforcement learning has great applicability potential in networking and clouds. It is already being used in multiple use cases, such as Wi-Fi signal optimization. We have reviewed the 2 significant groups of machine learning techniques: unsupervised and supervised learning. Reinforcement learning is a totally different category, since in this case there is not, as such, any data available. Data will be generated as an agent interacts with the environment. The outcome of such interaction will be in the form of a reward, positive or negative, and new state information of the environment, which will determine the following action to execute, and so on. The agent learns by trial and error. Alright, there we go. So we can do that like that.
The image you uploaded depicts a basic model of reinforcement learning, RL, a type of machine learning algorithm where an agent learns to make decisions by interacting with the environment. Here's how the components work together. Components explained. Agent. The agent is the learner or decision maker. It observes the state of the environment, makes decisions based on those observations, and receives rewards based on the actions it takes. Environment. The environment is the world through which the agent moves and learns. It provides feedback to the agent in the form of states and rewards. The environment changes in response to the agent's actions. State. The state represents the current situation returned by the environment. It's the context for the scenario in which the agent operates. The state can include everything the agent needs to consider to make the next decision. Action. Actions are the set of possible steps the agent can take from a given state. The trace of action affects the next state of the environment. Reward. A reward is feedback from the environment in response to the actions taken by the agent. Rewards can be positive or negative and are used by the agent to learn which actions lead to better outcomes. How it works. Interaction. The agent takes an action in the environment based on the current state. Feedback. The environment responds to the action with a new state and reward. Learning. The agent updates its strategy to maximize its long-term reward based on the reward received. Applications. Video games. In gaming, RL can be used to develop AI that adapts to player actions to either assist or challenge the players in strategic games. Autonomous vehicles. RL is used in the development of self-driving cars, where the system continuously learns the best maneuvers in real traffic conditions. Robotics. In robotics, RL helps robots learn complex tasks like walking, picking up and moving objects, or navigating through environments. Finance. For algorithmic trading, where the system learns to make trades based on historical data to maximize investment returns. Healthcare. RL can optimize treatment plans and manage resources in healthcare settings, adapting to the state of patients to provide personalized treatment. This model of reinforcement learning is crucial in developing systems that require a level of decision-making autonomy and is particularly powerful in scenarios where it is impractical or impossible to program all possible scenarios that might be encountered.
Alright, so moving on. There are many different algorithms, and we will not review them in the book, but I want you to understand some of the key fundamental concepts that are common to all. So the first one is Markov decision processes. In layman's term, the Markov property refers to the probability of a state depending only on the previous state, not on the following previous states. This leads to the concept of Markov chains, statistical models where the probability of an event is only dependent on the previous state. With this assumption, we have a new framework called Markov decision processes. This is the basic framework on which most reinforcement learning techniques rely. A Markov decision process not only defines the different states and the probability of changing to a new state, but also the possible actions that will lead to such state change and what the reward will be if it happens. The goal of the process is to maximize the accumulated rewards, and in that process, the agent will learn which are the best decisions to take at any point in time to maximize the reward. One key aspect of any reinforcement learning process is that it must learn from its mistakes. In other words, it needs to explore the space of actions to learn what works and what does not. For example, it needs data. On the other hand, once it learns, it needs to start using those that appear to be the optimal actions to maximize rewards. There is a somewhat conflicting goal. On the one hand, you want to make the right choices to maximize the rewards, but for that to happen, you need to make mistakes and explore. Since it is impossible to know when you have learned all you need, any reinforcement learning process needs a certain amount of exploration and exploitation of its developed knowledge through previous trial and error. Depending on the approach and algorithm used, reinforcement learning may use deep neural networks as part of the learning process. This is usually referred to as deep reinforcement learning. As I mentioned, reinforcement learning in networking and clouds can be applied to multiple problems, particularly those that potentially require a specific type of dynamic change or optimization. QoS and buffer depth configuration. You could think of an agent analyzing a number of variables from the network and optimally configuring the QoS or the interface buffer depths to minimize packet loss. Radio optimization in 5G cells, Wi-Fi power optimization in access points, VM or container placement in a cloud to optimize power consumption, etc. Those are all problems that reinforcement learning can be applied to. All right, so the key takeaway is over time, the most transformational use cases in networking and cloud will be driven by the applicability of reinforcement learning techniques. Okay, so the next section is causal inference. The machine learning methods we have reviewed so far are discovering relationships in the data. In one way or another, they identify linear or nonlinear correlations between different variables. However, no method so far can provide any causality. The methods explained work almost exclusively using the available data, but we must understand that the causes are not in the data. You need to have a scientific model that provides contextual information. No purely data-driven method can derive or obtain causality. Causality can only be inferred by leveraging domain knowledge provided by a domain expert. For example, human input. Correlation does not imply causality. If we have two variables, memory utilization and number of containers in our K8 cluster, and they have a Pearson correlation index of 0.85, all we can conclude is that they are highly related. However, just by looking at the data, it is impossible to know if one is driving the other or if another factor, aka confounder, is potentially driving the two. Therefore, it is necessary to have additional context information or domain knowledge to attribute any causal relationship. In that sense, causal inference is the discipline that complements the previous techniques reviewed, as it adds the ability to answer causal questions, not simply statistical ones. Those questions are about: what is causing the optical transceivers to fail? What will be the impact on the number of customer calls if we let the temperature 2 degrees higher in our data centers? However, causal inference differs from other machine learning techniques because it is not purely data-driven. It requires a model that captures the knowledge about the dependencies. This is called a structural causal model, SCM. It consists of two building blocks: a graph, more precisely a directed acyclic graph, DAG, that represents the causal relationships between the different variables in consideration. This DAG, which stands for directed acyclic graph, is built with domain knowledge, a set of equations that mathematically express the nature of those relationships captured in the graph. So let's see what ChatGPT has to say about this, which if it has to say a lot about this, that's impressive.
The diagram you uploaded represents a simplified model of how different variables are interconnected within a system, likely related to a technology or service environment. This model uses directed edges to show dependencies or influences between variables. Components explain number of customers. This note suggests that the number of customers influences both memory utilization and number of containers. This can imply that as the customer base grows, the resources required, memory and container instances, increase. Memory utilization. Memory utilization likely represents how much RAM or other memory resources are being used in the system. The model suggests that this is influenced by the number of customers, which makes sense if each customer's activities consume system memory. Number of containers. The number of containers could refer to instances in a cloud environment, like Docker containers or virtual machines. This variable is also shown as being dependent on the number of customers, indicating that more containers may be needed to handle more customers or their data workloads. Interpretation and applications. Scalability analysis. This diagram could be used by a cloud service provider or within an enterprise to model how resource needs change as the number of customers increases. Understanding these relationships helps in planning for scaling resources efficiently. Performance monitoring. By analyzing how increases in customer numbers affect memory and container usage, IT teams can better anticipate performance bottlenecks and address them before they impact service. Cost management. For businesses, understanding the relationship between customers, memory utilization, and container deployment can aid in predicting costs associated with infrastructure needs, leading to more accurate budgeting and financial planning. Practical usage. In a real-world scenario, such as a cloud-hosted web application, this model can help in auto-scaling strategies where, based on the number of active users, customers, the system automatically scales up or down its container instances and adjusts memory allocation to maintain optimal performance and cost efficiency. This type of modeling is essential in systems engineering and resource management, especially in environments where resources are elastic and need to be managed according to demand dynamically.
All right, so the arrows in the DAG relationship, which stands for dynamic acyclical graph. Yeah, and we can understand what that means because this is a graph and it's acyclical. So this is pointing here, but there's no loop back to that, so it doesn't. So I think that's probably what that means. The arrows in the DAG represent the direction of the causal relationship. The diagram can be interpreted as a Bayesian network where the edges simply represent the existence of a connection. When the edges have an arrow at the end, it represents the existence of a causal relationship, so we can refer to the diagram as a causal network. With the above model definition, it is possible to evaluate the impact of certain variables in others given, or adjusted for, or conditioning on another variable which we call a confounder. In our example, we could quantify the impact of the number of containers in the memory utilization adjusted for the number of customers. There are specific methods and techniques to extract causal relationships from the data itself. These methods do not guarantee, in general, a good outcome. The well-accepted consensus is that data is just not enough to obtain causal relationships. A direct input from the context domain knowledge is required to identify such relationships correctly. Key takeaway: correlation does not imply causality. It's almost impossible to derive causality just by looking at the data. A human-defined causal model is required. All right, so the next section is natural language. And this is processing, NLP. I find quite accurate the definition in Wikipedia about natural language processing. Natural language processing, NLP, is a subfield of linguistics, computer science, and artificial intelligence concerned with the interactions between between computers and human language, in particular, how to program computers to process and analyze large amounts of natural language data. NLP includes lots of techniques well beyond the scope of this book. However, there is undoubtedly an area of NLP that takes advantage of statistical and machine learning methods that interest us. Those are applied for the analysis and synthesis of natural language and speech. Use cases such as natural language understanding, speech recognition, natural language translation, natural language generation, text summarization, text classification, text captioning, style recognition, fake content detection, chatbots, etc., are all NLP applications where there is a strong dependency on using machine learning techniques. Why is NLP relevant to you? Since we are talking about networks and clouds, a good amount of the data a network and cloud engineer needs to deal with on a daily basis is natural language. A log message, they have been in most of the cases designed for human consumption. Configuration files of network devices, they use forms of natural languages such as iOS, EOS, Junos, etc. The output of a CLI command, interface description fields, domain names, alerts generated by systems are frequently generated with the expectation that a human will read and act on them. Metadata, tags or labels, usually strings intended to provide contextual information to some other data. Customer messages in support tickets, customer feedback on your SaaS service, software as a service, tweets from users or customers to your company's support Twitter account. These are just some examples of data you will likely deal with daily, which can be subject to NLP, natural language processing to extract information and turn it into actionable. We will review applied examples of the above in the practical use cases section of the book. However, for now, we must understand some of the basics of NLP, at least in what is relevant to us. We will not review certain areas that, while also exciting and definitely applicable in the context of ML, machine learning, are not fundamental to our scope. These are speech recognition or speech generation, natural language understanding, and its applicability to chatbots. All right, so the next section, and I'm on the over a half hour, but I've got some time this morning. The nature of natural language. Natural language in its written form, we will not tackle the verbal or spoken form, is nowhere near a form factor that machine algorithms can process. There will be, depending on the use case, several tasks or transformations required to put the data in a format that is adequate for analysis we intend to do. Somehow, we need to turn the text into some numeric representation that can be used to feed an algorithm. However, what kind of numeric representation do you create from a text? Various options will depend on what we want to accomplish. We first need to decide what our minimum unit of information is. What is the smallest symbol we want to represent? Is it a letter? Is it a word? Is it an n-gram, a series of continuous either letters or words? Whatever our choice is, this will become our token, the unit that will help us represent the context of the text. Once selected, transforming the input raw text format into a sequence of tokens is called tokenizing. In the different machine learning software frameworks and NLP libraries, we will find predefined tokenizers to help us perform this function. At this point, we have a sequence of tokens, but this is yet to be a representation that a machine learning model can consume. We need to turn this into numbers somehow. The data representation will significantly depend on the use case and what we want to accomplish. Let's take as an example that our goal is to classify or cluster texts. We need one mechanism to characterize the texts as a whole and to be able to compare and analyze them with other texts. Texts may have different lengths, so we need a representation independent of the text length. One prevalent representation for this type of use case is the concept of a bag of words. It is as simple as counting how many words of each type are on the text and representing that information in a vector. However, before that, we need to create a vocabulary out of all the words present in our input data. It may be all, or it may be the top N words, etc. This dictionary becomes our mapping mechanism between text and numeric representations. Each word has an index associated in the dictionary. Alright, so let's see what ChatGPT says about this.
The diagram you provided illustrates a process used in natural language processing, NLP, to extract and index significant words from a collection of text data. Here's a breakdown of each step and its significance. Components explained. Input data. This consists of multiple texts, text 1, text 2, text n. Each piece of text is a document or data entry that will be processed. Top N words. From each text, keywords are identified. These are typically the words that are most frequent, relevant, or otherwise deemed important based on the context of the analysis. This might involve statistical measures like TF-IDF, term frequency, and document frequency, which helps in identifying words that are important in a particular document relative to a collection of documents. Word dictionary. This is a mapping of words to indices. Each unique word from the collected top N words across all texts is assigned a unique index. This dictionary is crucial for transforming textual data into a numerical format that machine learning algorithms can process. How it works. Extraction and normalization. Words are extracted from each text and may be normalized by converting them to lowercase, removing punctuation, and possibly using stemming or lemmatization to reduce words to their base forms. Word selection. Algorithms identify the top N significant words from each text. These words are chosen based on frequency, relevance scores like TF-IDF, or other statistical methods that assess the importance of words within the text and across the text corpus. Indexing. The selected words are then indexed in a systematic way in the word dictionary, which serves as a lookup to quickly identify and locate words within the numerical data structure used in subsequent processing. Practical applications. Text classification. This setup is often used in text classification tasks where texts need to be categorized into predefined labels based on their content. The word dictionary helps in converting text to a fixed size vector that machine learning models can understand. Sentiment analysis. In sentiment analysis, the frequency and presence of certain words in the dictionary can determine the sentiment expressed in text. Machine translation and topic modeling. The indexed words and their representation allow models to learn about word associations and context, which are crucial in tasks like machine translation and topic modeling. Conclusion. The process shown in your diagram is foundational in many NLP applications. By converting text data into a structured, numerical format, various machine learning and deep learning models can efficiently process large volumes of text data for insights, predictions, and automated decision-making. This approach facilitates a wide range of applications in areas such as customer service, legal document analysis, content recommendation, and more, helping to bridge the gap between raw text and actionable intelligence.
All right, that sounds good. So once the dictionary is built, we can use it to transform each input text into its corresponding bag of words, numeric representation. It will be a vector with the length of the dictionary. Each position in the vector will represent the number of words found in the text for the word matching the index in the dictionary. At this stage, based on the choices we have made, we have a numeric vector representing the content of each input text. We have already seen earlier methods to compare vectors and compute their distance or similarity.
The diagram you uploaded illustrates a bag of words model used in natural language processing to convert text data into numerical vector form for analysis. This representation is crucial for many machine learning models that require numerical input. Here's a breakdown of the process. Components explained. Input data consists of multiple texts, text 1, text 2, text n, each being a document or data entry. Bag of words. This is a simplification where the text is represented as a set of its words, disregarding grammar and word order but keeping multiplicity. Vector representation. Each text is converted into a vector. The length of the vector corresponds to the number of entries in the word dictionary. Each position in the vector represents a word from the dictionary, and the value of that position represents the frequency of the word in the text. How it works. Text processing. Each document is first processed to extract words. This process typically involves cleaning the text, normalizing it, like converting alt text to lowercase, and removing stop words, common words that are usually filtered out. Dictionary creation. The dictionary is created to map each unique word to an index. This dictionary has all the unique words from the entire corpus, all the documents. Vectorization. For each document, a vector is created where each index corresponds to a dictionary word. The value at each index is the count of how often the corresponding word appears in the document. Example of vectorization. Suppose the dictionary created from alt text is hello, 0, cloud, 1, future, 2, computer, 3, network, 4, Oz, 5 for a document, hello cloud hello. The vector would be 2, 1, 0, 0, 0, 0, where hello appears twice in cloud once. This representation is sparse as most of the vector elements are 0, especially with a large dictionary. Practical applications. Text classification. This model can be used to classify documents into categories. Each document is represented as a vector, and machine learning models like Naive Bayes or SVM can be used to classify documents based on these vectors. Information retrieval. The bag of words model can help in designing systems that retrieve documents based on keyword searches, where documents are ranked based on keyword frequencies. Sentiment analysis. By analyzing the frequency of certain words, models can determine the sentiment expressed in text, such as positive, negative, or neutral. Limitations. Context loss. The bag of words model does not capture the context or the order of words, which can lead to loss of meaning that depends on the sentence structure. Sparsity. The resulting vectors are very sparse, mostly filled with zeros, which can be inefficient for computation. Conclusion. The bag of word model is a foundational technique in NLP for converting text to numerical data. It allows various machine learning algorithms to perform tasks like classification, search, and sentiment analysis on textual data. However, more sophisticated models like Word2Vec or BERT might be used to capture more nuanced semantic meanings by considering word contexts.
Okay, so that looks good. In particular, in the case of vectors representing words, We have identified cosine similarity as a pretty effective technique to quantify semantic similarity. Let's consider the following case. Text 1 has certain predominant words: network, cloud, EVPN. Text 2 has the same words in similar proportion, but maybe overall 2 times to 3 times total quantity because text 2 is much longer than text 1. Both texts probably address the same topic. Mathematically speaking, the angle between both vectors will likely be minimal, which means the similarity will be very high. We can intuitively see that a small angle corresponds to a similar text theme. Bag of words is an excellent basic representation technique, but it has limitations. Any positioning information about the words is lost. All that contextual information is essential in order to be able to do a more detailed semantic analysis. However, it is okay to ignore it if the purpose is simply to classify or cluster the text as a whole. Nevertheless, even for this use case, you could think that if a word is present in many or all texts, its significance is lower. On the other hand, if a word is only present in a few texts, that word may be more relevant and provides more specific information. However, the degree of information of each word is inversely proportional to the total number of documents it is present on. TF-IDF, term frequency inverse document frequency, is an enhancement from the basic count approach where, in addition to counting how many times a word is present in a document, it is weighted inversely by the total number of documents the word is present. This is a beneficial technique that helps augment the significance of specific words while minimizing the impact of others and producing more accurate vector representations. Suppose the purpose of the text analysis is to do some type of prediction or translation, summarization, or extraction. In that case, we need a more detailed context, which requires preserving the sequence information of the text. That means, from a data representation point of view, a text becomes a matrix. And I do have a question for the AI, but I'll get the answer to this first.
The image you uploaded illustrates a one-hot encoded matrix representation of a sentence commonly used in natural language processing (NLP) to handle text data. This form of representation is crucial for many machine learning models that require numerical input rather than raw text. Here's a breakdown of the process and its implications. Components explain. Sentence. The sentence EVPN is used in the cloud fabric is broken down into individual words. Matrix representation. Each row of the matrix represents one word from a sentence. Each column corresponds to a position in the vocabulary of the text corpus, which in this case is likely limited to the unique words in the sentence itself. 1 in column indicates the presence of that word at that position in a sentence, making this a one-hot encoding where each word is represented as a vector of zeros with a single one. How it works. Vectorization. Each word in the sentence is converted into a vector. The length of the vector is equal to the number of unique words in the sentence, or potentially in the larger vocabulary being used. In the matrix, each row represents these vectors. One-hot encoding. In these vectors, A1 is placed in the index corresponding to the word's position in the vocabulary, and 0 fill the other positions. This method effectively captures the presence of words but not the order or any contextual relationships. Practical applications. Input for models. This type of data representation is used as input for various machine learning models in tasks like text classification, sentiment analysis, or even more complex deep learning models that require a numerical representation of text. Feature engineering. In NLP tasks, such matrix representations can serve as basic features from which more complex features, like word embeddings, might be derived. Limitations. Scalability. One-hot encoding can become very inefficient as vocabulary size increases because the vector representation becomes very sparse and large, which can lead to high memory consumption. Lack of context. This method does not capture any semantic meaning or the relationship between words. Words that are similar semantically will have completely orthogonal vectors. Fixed vocabulary. The method requires a fixed vocabulary, and handling words not seen during training out of vocabulary words can be problematic. Conclusion. The one-hot coding depicted in your diagram is a foundational technique in NLP for transforming text into a form that can be processed by algorithms. While it's a starting point for many applications, more sophisticated methods like embeddings are often used in practice to capture deep linguistic patterns and reduce dimensionality. This method is instrumental for basic tasks and serves as a stepping stone toward more advanced NLP techniques.
All right, so that was good. Now I do have a question. For you now. So the question is, when it comes to words, in this context, there exists a approach called TF-IDF, term frequency inverse document frequency, and it's an enhancement from the basic count approach. So tell me, according to these approaches, like what are the top 10 words with the most amount of meaning?
The concept of term frequency inverse document frequency, TF-IDF, is designed to reflect how important a word is to a document in a collection or corpus. It enhances the basic count approach by diminishing the weight of terms that occur very frequently in the document set and increasing the weight of terms that occur rarely.
Oh, it just depends on the document.
Here's how TF-IDF works. Term frequency, TF, measures how frequently a term occurs in a document. Since every document is different in length, it is possible that a term would appear much more times in long documents than shorter ones. Thus, the term frequency is often divided by the document length, aka the total number of terms in the document. As a way of normalization, TF-T equals number of times term T appears in the document, total number of terms in the document, TF-T equals left, frac X, number of times term TX appears in the document. X, total number of terms in the document, right, TF-T equals total number of terms in the document, number of times term T appears in the document, inverse document frequency, IDF, measures how important a term is. While computing TF, all terms are considered equally important. However, certain terms, such as, is, of, and, that may appear a lot of times but have little importance. Thus, we need to weigh down the frequent terms while scaling up the rare ones by computing the following. IDF T equals log total number of documents with term T in it. IDF T equals log left frac X total number of documents. X number of documents with term TX in it right. IDF T equals log number of documents with term T in it total number of documents. When you combine these two metrics, you get the TF-IDF score of a term in a document, which is simply the multiplication of TF and IDF. TF-IDF T equals TF T times IDF T TFX IDF T equals TF T times IDF T TF-IDF T equals TF T times IDF T. Top 10 words with most meaning using TF-IDF. Identifying the top 10 words with most meaning using the TF-IDF approach will require analyzing specific document sets since TF-IDF is contextual to the document corpus used. However, in general, words that have high TF-IDF scores across various documents and corpora tend to be terms that are uniquely relevant to the subject matter of the text but are not common across all texts. For example, in a corpus of medical research papers, high TF-IDF scores might be found for terms like neuroplasticity or oncology because they are specific to particular studies within the medical field but not used commonly outside specific research contexts. For an accurate list tailored to a specific corpus, you would need to run a TF-IDF calculation across your dataset. The algorithm would then highlight the terms that are particularly characteristic of the documents in that set, distinguishing them from general vocabulary.
All right, so I guess I'm asking about your training specifically, which, from what I understand, basically comes from the internet. So, like, according to your training, what are the top 10 words with the highest TF-IDF score?
My responses are generated based on patterns learned from a vast range of text sources on the internet, but I don't have a predefined list of words with the highest TF-IDF scores across all these sources. However, I can explain which kinds of words typically yield high TF-IDF scores. Specialized terms, words that are very specific to certain fields or topics, such as neuroplasticity, medicine, or polymorphism, programming. Proper nouns, names of people, companies, organizations, or specific events, such as Tesla, Amazon, or Brexit. Technical terms, words used in specific industries, such as containerization, software development, blockchain, finance, or isomerization, chemistry.
Okay, so what about for, like, if you're going to name a business, would you want the name of your business to have a high or a low TF IDF score? Okay, it depends on your goals. Of course, they're always going to say that. Yeah, it's just the uniqueness of the name. Alright, whatever. I'm not going to listen to that. So, on the other hand, if a word is only present in a few texts, the... Oh, you know what? Okay, so this is where I am. Now we have a numeric representation of a sentence that preserves the order information of each word and maps each to a dictionary. With this, we can work on ML algorithms. One challenge of this representation is that the dictionary is still simply a flat list of items that are apparently unrelated to each other. Every word has a different position in the dictionary, but the fact that two words are contiguous in their indexes has no specific meaning since there is no specific ordering. We have no clear way to make connections like apple and orange being somehow closer to each other than to chair because they are both fruits. Oh, but I mean, we have the biology tree of life. Like, we can make connections like that based on their evolutionary path. Like, we know all that. We need more advanced representation mechanisms that may have some semantic awareness so that the analysis we do considers semantic similarity. Somehow we need a new space to represent the words that extract information from them. At this point, probably some of what we have seen in earlier sections of the book may resonate. Remember the concept of latent space of the encoder-decoder architectures, which represent a more compact and informationally dense representation of the data. Let's leverage such concepts. Let's suppose that we train a model like the following. And one thing I was curious about as well. Oh, do I have this? I don't.
The diagram you provided illustrates a basic setup for a type of neural network training method commonly used in natural language processing, NLP, particularly for models like BERT, bidirectional encoder representations from transformers. This approach is known as the masked language model, or MLM. Here's a breakdown of how it works and its importance. Components explained. Input sentence. EVPN is used in the XXX fabric. Here, the word cloud is replaced by XXX, a mask. This masking forces the model to predict the original word at this position based solely on the context provided by the other words in the sentence. Encoder. The encoder processes the input text. In architectures like BERT, the encoder consists of multiple layers of transformers that help the model understand the context of each word within the sentence. Latent space. The output from the encoder represents the encoded information of the input sentence in a higher dimensional space, latent space. This encoding captures the contextual relationships between words. Decoder. The decoder's task is to predict the original word that was masked out. In many transformer-based models like BERT, the encoder output directly serves as input to a prediction layer without a traditional decoder structure used in other types of models like Seek-to-Seek. Output. The model outputs a prediction for the masked word. In this case, the correct prediction would be cloud. How it works. Training. During training, the model learns to predict the masked word based on the context provided by other words in the sentence. Typically, a certain percentage of words in each input sentence are randomly masked, and the model learns to predict these words accurately. Objective. The objective is to enable the model to develop a deep understanding of language context and word relationships, which improves its performance on a variety of NLP tasks. Applications. Language understanding. Models trained using this method excel in tasks that require a deep understanding of language structure and context, such as sentence completion, text summarization, and question answering. Fine-tuning for specific tasks. Once pre-trained on large corpus using the MLM approach, models like BERT can be fine-tuned with additional output layers to perform specific tasks like sentiment analysis, named entity recognition, NER, and more. Importance. This training methodology allows the model to effectively learn language context in a bidirectional manner, meaning it gathers insights from both the left and the right context of a masked word. This is crucial for understanding the intent and meaning of language, significantly enhancing the model's ability to handle complex language tasks compared to older models that may only consider unidirectional context or simple patterns.
All right. What was the other thing I was curious about? It had to do with something I was reading here. Oh, I just wanted to demo the evolutionary tree of life. Yeah, so this is my favorite one. It's onezoom.org, and it's so the tree of life is it's how people, the species share common ancestors. So it goes. Let's stop zooming in, please. How do I go back? I wish it wouldn't have zoomed in automatically like that. Okay, so now I can hit pause. There we go. And now if I click on all of life, how do I zoom into it? I guess this one's, maybe there is a better one out there than this one. This one's very hard to use. So here's one. Well, I guess this one's the best. There really isn't a better one out there. So let's search for Apple. Okay. There we go. And then let's duplicate the tab and then search for orange. So you can see it should be pretty easy to form connections this way. So let's do a California, well, let's just do a Mexican orange because that's the first one. So we can already see apples and oranges are quite a bit different. Yeah, so alright, so there's the Mexican orange, which does not look like an orange to me. Let's do a sweet orange instead. There we go. Yeah, so quite a bit different for sure. We can open them up. This takes us to the Wikipedia page. So you can see like this stuff is all mapped up. So it should, that would be a good way to, I think, train an AI model based on the evolutionary tree of the species. All right, I'm at the 8:40 mark. I'm at about the hour mark, and I was going to take a few minute break. So I feel like it's just a good natural stopping point. So, yep, I'm going to stop the video. Thanks for watching, and see you in the next one.